Morning, everyone. So I guess let's wait for another maybe 1 or 2 minutes. So today, mostly I'm just gonna finish up, the NPG explanation and then do a quick review on all the policy optimization approach that we covered so far, right? And then a very quick intro of a slightly new variant of policy optimization. And then starting from Thursday, we're just gonna move to a new topic where we try to see how we can actually learn from demonstrations, right? So the setting will be more applicable in the sense that as an expert, I just show the robot how to, for instance, play a field table tennis, and then the hope is that the robot can learn from demonstrations, right? So that's we will talk about several approaches to do that starting from Thursday. And one particular approach is nice in the sense that, imagine you're trying to sort of teach a robot to play tennis, and it's really hard for us to, write down those cost function or objective function. Like I don't know how to write it down a cost function, right? For robot playing table tennis. Like, what does this mean? Does it mean that you have to hit a ball at that particular speed, at that particular height, with that particular spin? Like, we don't know, right? But what we can do is just show demonstrations for the robot. And the hope is that maybe the robot can figure out the cost function that the human is actually trying to optimize in their mind, right? And once you reverse engineered out this cost function, then you can apply control methods or reinforcement learning methods, right, to learn a policy for playing table tennis. So that's what we will cover, next week. Okay, so for today, let's just wrap up, policy optimization approach. Okay, so let's start. Okay, so let's just do a quick recap on natural policy gradient, right? So this is an approach that you're implementing in your homework, right? So it shouldn't be that too hard for the homework implementation for this one, right? And you will see actually this is pretty fast in terms of solving that particular simulation, right? Feel free to compare NPG versus, the regular policy gradient, because along the way you implement NPG, you already implemented the policy gradient, right? Like, forget about the Fisher information matrix, run your code using policy gradient that you developed, you implemented, and compare the performance of policy gradient to the performance of natural policy gradient and see how they compare, right? Try to get a sense of, the advantage of NPG from a practical perspective, right? So the motivation behind NPG is that is literally from this optimization framework, right? So if you look at this objective function, the objective function says that we want to maximize the local advantage, right? So given the current policy pi theta t, I want to find a new policy that is very greedy in the sense that maximize the advantage against the older policy, right? Averaged over the older policy state distribution. And we know that if we just do that, this is not good, right? Because approximate policy iteration, remember the oscillation phenomena that we talked about for just doing this greedy policy optimization, right? So what we did in the CPI and what we did in this NPG is that let's add a distress region constraint, right? So this says that I want to be greedy, but I want to make sure that my new policy is actually not too far away from the older one, subject to this KO divergence, right? And this rho is the trajectory distribution. Right. And then what we did is that, we think that, this constraint optimization problem is pretty complicated. Well, first of all, this objective function is nonlinear, right? It's potentially non-convex, depending on your parameterization of the policy. And second, this KO divergence is pretty complicated, right? In the sense that this relies on trajectory distribution, which we don't even know how to implement and evaluate that, because we don't know the transition dynamics, right? Okay, so what we did is let's just do a convexification of this optimization program, right? And let's particularly just do first order Taylor expansion of the objective function and then do second order Taylor expansion on the KO divergence. So if you do that, our objective function becomes a linear objective function, right? So this is the inner product between the policy gradient and the change on the parameters, right? Which is theta minus theta t. So this is nice. It's a linear objective function, right? So this is just a PG. Right? And the constraints is also nice. It just becomes a quadratic symmetric constraint, right? Where this, this matrix F is what we call the Fisher information matrix, right? So inside the expectation, this is always positive semi-definite. So the matrix is hopefully, the matrix should always be semi-definite, and hopefully, this could be a positive definite matrix as well, right? And if not, you just add some regularization, right? That's what that's a hyperparameter that you would turn in practice. All right, so now we get to a nice place where we have a linear constraint and a quadratic. We have a linear objective and then we have a quadratic constraint, right? And what we didn't really cover last week is that how we get from this simple constraint optimization problem to this closed form, very simple one-line update. Right? So particularly the one-line update says that I'm gonna, precondition my gradient, right? Instead of following the gradient, I'm just gonna precondition it in the sense that I left multiply the matrix inverse, the Fisher information matrix inverse, right? Okay, so that's what we covered last Thursday, right? And we spent a lot of time talking about how to do this, right? We did a lot of multivariate calculus, and we realized that, second order Taylor expansion is actually, the outcome of the second order Taylor expansion is actually pretty simple, right? It just, the first order term goes away because the gradient is always 0. The zeroth order term is always 0 too. And what we left is this pretty simple, second order term, right? So the Fisher information matrix is the Hessian of this KO divergence constraint. Okay, so now let's talk about how we get to this, very simple one-line closed form update, right? This NPG update. All right, so that's what we're gonna do today. Any questions for now? Sorry about that. Okay. All right, so these are the three things that we're gonna do today. So we're gonna derive the closed form solution for this NPG update. Right, and the second thing we're gonna do is trying to explain and intuitively see, why NPG is actually making sense. Right, and then the third part is that let's just do a quick review on the policy optimization approach that we covered so far. All right, and at the end, I'm gonna introduce a very simple new variant of the NPG, right, which is also very practical and which is also what people use nowadays as well. All right, so that's the the plan. Let's see if we can go through all these 3 points today. All right. All right, let's talk about how we get this closed form solution once we get to this very simple optimization problem where the objective function is linear and the constraint is quadratic. All right, so at this stage, you should convince yourself this is not super hard because my objective function is linear and my constraint is a quadratic, which is convex. And this is at most a convex optimization problem, right? There should be a global optimal solution for this, right? And even nicer is that we just have linear constraint and we have quadratic. We have linear objective and we have quadratic constraint. So hopefully that gives us a closed form solution for the global optimality. All right, so to do that, let's just first do a field notation simplification. All right, so I'm just rewriting everything in terms of these 2 new symbols. So particularly what I did is that let's just denote this as this nebula symbol, this gradient symbol. And instead of optimizing theta, let's just optimize the difference between theta and theta t. So let's call it delta, right? And let's just write the Fisher information matrix is the symbol F, right? So that's, I just replaced, I just simplified these notations. So now instead of optimizing theta, I'm optimizing the change, right? What's the change that I should apply? What's the delta that I should apply on theta t, right? So nothing is fancy here. I'm just rewriting things using different notations. Right? And now I'm going to do this change variable trick, right? I'm going to define something called tilde delta, which is written as the square root of this Fisher information matrix times this vector, change vector delta. Right? So F1/2 is the square root of this positive definite matrix. Right? So if you can recall the eigen decomposition, right? So if I can write F, using its eigen decomposition, U sigma U transpose, right? So then F1/2 is just U of square root of this diagonal matrix sigma U transpose, right? So that's what square root of F means if F is a positive definite matrix, right? So in other words, F square root of F, yeah. So in other words, F1/2 square is just F. All right, so I'm just to introduce a variable tilde delta, and I'm now gonna rewrite everything in terms of this new variable tilde delta. Right, so that's what I'm gonna do. So for this constraint, now things becomes pretty easy because I can just write this as F1/2 times F1/2 times delta, right? So this is F1/2 delta transpose F1/2 delta, which is tilde delta transpose times tilde delta. So that's how I get my constraint, right? And for the objective function, let's just do this trick. I'm just multiply F square and then immediately multiply F negative 1/2, right? Times delta. So this is an identity matrix, right? So this means that this becomes F1/2 gradient transpose times tilde delta, right? So I just did this to, change of variable trick, right? I'm just rewriting everything in terms of tilde delta now. So now this is pretty nice, right? So I get an objective function, which is again linear, and my constraint is actually saying that the norm of my vector tilde delta should be less than delta, right? Should be less than this small delta. So this is a ball constraint, right? I'm constraining my variable tilde delta in a ball with radius square root delta, square root little delta. So in other words, this is what my constraint represents, right? So every point here, every vector here corresponds to a tilde delta, right? Because what I said is the norm of tilde delta is less than square root delta, right? So this is the constraint representing tilde delta, right? What's the objective function looks like? So the objective function says that I care about the inner product between a vector inside this ball and this red vector, right? So this red vector is the vector in my objective function, right? Okay, so now our goal from this picture, right? Our goal is to pick a vector inside this ball such that the inner product between this dashed line and this red line, which is the vector f square root, which is the vector of f negative 1/2 times the gradient, right? We wanted this two inner product to be maximized, right? So from this picture, it is easy to see that the vector that maximizes the inner product, right, is actually this guy. Right? Does that make sense? So I have this target vector, right? And I'm trying to find a vector such that this a green vector such that the inner product between the green vector and this red vector, that red arrow, right? They're maximized. But I have a constraint saying that this green vector, this green line, needs to stay inside this ball. Yes, I said there's a question.
But the target vector itself is variable, right? Like it could be any one of those vectors in that bowl.
No, this is fixed, right? This is our policy gradient at the current policy parameter theta t.
Oh, right. It's
right. So this is facial information matrix, right? Remember, f1/2 negative. We just write this like, so yeah. So this is f theta t 1/2 times.
Okay, yeah.
Policy gradient, right?
Yeah, I thought it was the gradient.
This is a vector defined by theta t, right?
Right. Yeah.
So this is a fixed vector, right? So that's why this red arrow, that one is always fixed.
Yep.
Right. And now I'm just searching over inside this ball such that the vector, the green vector, the inner product between this green vector and the red vector is maximized, right? And from this picture, it is obvious that this vector, the green vector that is in parallel with respect to this red vector, right, is the potential maximization solution. And in order to get the maximum solution, we just scale this green vector all the way such that the tip hits the ball surface, right? That's the maximum you could do. That's the best you could do.
So in that expression, you're taking the gradient with respect to theta of j of theta sub t.
Yeah, so remember, this is a short notation for gradient of theta, j theta measured as theta equals to theta t.
Okay.
This is just policy gradient at my current solution, right?
Yep. That makes sense. Thank you.
All right, so which means that the delta, the maximum tilde delta should be a vector that is in parallel with respect to this red vector, right? And the parallel means that it's just a scalar times this vector, right? And we need to figure out this scalar so that the norm of this green vector is actually equals to square root delta, right? Because the radius is square root little delta, right? So in other words, this is tilde delta max, right? So in other words, we wanted this red vector to be scaled all the way such that the tip just hits the surface of the ball, right? Which means the norm of this green vector should be square root of little delta. That's what this expression is saying, right? So that allows us to solve the scalar eta. So if we just solve the scalar eta, this gives us this familiar expression that we had, right? This is the expression that we use for learning rate. Right, so plugging in back, this gives us an expression for this green vector, this tilde delta. Right, so now we get an expression for this tilde delta. And the last step to do is actually map tilde delta back to the delta, right? Because delta is the parameter that we actually care. So remember, tilde delta is defined as f1/2 of delta, right? Which means delta is actually equals to f1/2 inverse tilde delta. Right? If you just do that, this gives us the closed form solution for the change that we want to make on the parameter theta, right? Right. So this is the familiar, NPG update. Right. So we sometimes sort of take a detour so that we like introduce this variable tilde delta, right? The reason that we do that is that now our constraint from this geometry perspective is pretty simple, right? This is just a ball with radius square root little delta, right? And it allows us to reason, just from the geometry, it allows us to reason what's the maximum vector that realizes, the inner product, what is the vector that maximizes the inner product, with respect to this red vector, right? And then the last step is that let's just change the tilde delta back to delta, right? And that's all we did. So we just rescale everything so that we can put a constraint inside a ball, which allows us to do very simple reasoning just in geometry, right? And then let's just scale everything back to the original coordinates.
So if the length of f inverse half delta, so yeah, if the length of that red vector was inside the bowl, then you'd have to pick a vector like shorter than length delta, right? Is that possible?
No, right? Yeah.
Oh no,
yeah. So think about this, right? Okay. So good question, right? So let's see. My red vector is actually this guy.
Oh yeah, you'd still pick the
right. Okay. So if my red vector, to think about the red vector to be this new dashed vector, right? What's the vector that achieves the maximization in inner product with respect to this new red vector?
Yeah, you'd still pick the one that's equal to radius.
It will be still this one, right?
Yeah.
So you're always going to hit the surface of the ball, right? Because you want to maximize the inner product, right? To maximize the inner product, let's just scale, make the norm of the vector as big as possible, right? So we should always hit the surface, right? And we should always make sure that the angle between these two vectors, theta is equal to, I don't want to use notation theta, such that the angle, this alpha, is always equal to 0, right? We want these two vectors to be in parallel, right? Because that maximizes the inner product. And then we scale this green vector's norm as big as possible, right? That should be the solution that achieves the maximum inner product.
And if the red vector for some reason is the 0 vector, then
then everything is 0, right? Everything is optimal. Everything is the maximum because everything is 0, right?
Yep. So it doesn't matter. Yeah, you just pick so then it doesn't matter what green vector you pick.
Right. Okay, so yeah, so another thing to think about, another way to think about this picture is that, what's the inner product of two vectors, x and y, right? So this is just a norm of x times the norm of y times sine or cosine. This is a cosine of the angle between these two vector x, y, right? So to maximize the inner product, let's just make sure the angle is 0. So cosine is equal to 1, and make sure the norm is as big as possible, right? That's two ways to make sure the inner product is big. And that's what we did in this picture, right? Okay. Any questions for this derivation? Okay, so there's a way more standard and a straight way to do this using Lagrange multiplier, right? Which I'm not going to talk about because I think many of you probably haven't heard about this Lagrange multiplier thing. So maybe you did when you learn SVM, right? So there you probably talked about prime undo version of SVM. So you kind of touched this Lagrange multiplier, but I'm not gonna assume that you know this Lagrange multiplier. So a standard way to do this is just introduce a Lagrange multiplier, lambda, and put the constraints back to the objective function. And now you have this like min-max problem, right? And if you solve min-max problem, you get to this closed form solution as well. So this is standard and straight way to do that. So what we did in the previous slides is that, assume that I don't know Lagrange multiplier, right? So what's what's another way for me to solve this constraint optimization problem? And what we did is just we used sort of this we sort of scale the parameters so that now we can reason a ball constraint, which allows us to actually just find the optimal solution from a geometry perspective. Right, but this is like, the Lagrangian multiplier is a pure algebra approach. Right, so yeah, so as I said, this is optional, this is our scope. But, to just summarize, at this stage, we pretty much complete the NPG algorithm derivation, right? So we started from convexification of our nonlinear optimization problem, and we get to this very simple optimization problem, right? You should convince yourself, this is solvable, right? This is at most a convex optimization problem, so we should have a global optimal solution, right? And then, you can either use this very standard Lagrangian multiplier approach to get the closed form solution for this convex optimization problem, or you could do, the detour that we did from the previous slides, right? Where you're trying to find the optimal solution using from a geometry perspective. Okay, so that's the first part of today's lecture, right? Any questions so far?
Just out of curiosity, are there closed form solutions for higher order Taylor expansions of what we just did?
No. If you do third order Taylor expansion, right? So you have third order polynomial. So what's third order polynomial? It's not a convex optimization anymore, right? Right. So second order function looks like that, right? Third order function gonna look like that, right? Yeah. So you're doing non-convex optimization. So third order polynomial is already becomes hard. Right.
I have a question. We just went over like how to set eta, right? But to tune to set delta, we just like tune it basically as a hyperparameter.
Yeah. So that's a hyperparameter you tune, right? But I said like delta is actually intuitively is easier to tune because this is a KO divergence between two distributions, right? Like learning rate is it's not super intuitive to tune because learning rate depends on your parameters of your neural nets, right? Like if I scale my parameters, if I rotate my parameters, like your learning rate, like I don't know how to actually like properly deal with my learning rate, right? Like imagine today I use a different, unit. Maybe I use meter in my parameters. Tomorrow I used, whatever other metric in my parameters, right? Like it's very hard to tune sort of the learning rate corresponding to the parameters. But regardless of what parameterization you use, KO divergence is just still defined as a KO divergence between two trajectory distributions, right? So like this is invariant of your parameterization. You could use a neural network, you could use decision tree, right? But the result is still distribution. This is just still KO divergence between distributions, right? So intuitively, this is easier to tune than tuning the parameters because we don't know the physical meaning of these parameters for a neural network, for instance, right? Like we don't, it's just black box parameters, right? Okay, so now let's talk about some of the explanations for NPG. Right, so a detailed, thorough explanation, derivation of NPG or natural gradient is out of scope, but let's try to see, if we can get some big picture from this natural gradient or natural policy gradient. All right, so this is the update, right? So this is called natural gradient. It is the matrix product of the inverse of Fisher information matrix and the gradient. Right, so we derived this formulation from a KO divergence perspective, right? And we said that KO divergence is a complicated divergence quantity, but if you just do Taylor expansion, we find that up to second order, right? So this KO divergence is nothing but just this very simple quadratic constraint, right? And it's symmetric. Right, so this is a metric as well, right? Because f theta 0 is positive definite. Right, so this is a distance metric, right? like, we can use Euclidean distance, but like no one says that Euclidean distance is, the best distance that we should use, right? So this is a valid distance metric too. That measures the distance between theta and theta 0, right? Right, because if theta and theta 0 are close to each other, if theta and theta 0 are equal to each other, then this quantity is 0, right? If they're really far away from each other, this quantity is also really big. So this is a valid definition of distance, right? And no one says that, Euclidean distance should be the best one to use, right? It's just very convenient to use Euclidean distance, but it's not necessarily the best, right? All right, so our goal here is actually to make sure the two distributions between the two policies, right? They do not change too much. Right? That was our goal, right? That's what we did in CPI as well. But like that doesn't mean that the parameter theta cannot change too much, right? Like making the small change on parameter theta ensures that the two distribution resulting from the two policies won't change that much, but not vice versa, right? I could still make very big changes on theta, but my two distribution could potentially be small. The difference between two distributions potentially could be small. All right, so to get this intuition, right, let's look at this particular example. So now I'm just making things very simple. Let's look at a special case where this Fisher information matrix is actually a diagonal matrix. All right, let's put everything in 3 dimensions. Right, so this Fisher information matrix is just very simple diagonal matrix where I have sigma 1, sigma 2, sigma 3 on the diagonals. Right, so then in this case, the Fisher information matrix inverse times the gradient. Right, so this is just 1 over sigma 1 times gradient theta 0, 1, right? 1 over sigma 2 times gradient theta 0, 2, over sigma 3 times gradient theta 3. Right? In other words, I just scaled every coordinate of the gradient using the corresponding diagonal element, right? Okay, so we can just write this gradient update, this NPG update for every coordinate. For every coordinate I, this is my update step, right? So in other words, I'm actually scaling my learning rate by 1 over sigma I. Right, so this is kind of magic because now this is saying that instead of using a universal learning rate for every coordinates, I'm actually scaling every coordinate using the corresponding diagonal element in my Fisher information matrix, right? Like I have different learning rate for different coordinates. And one special case is that if there's one coordinate, sigma I, is tiny, then we indeed will have a huge learning rate, right? Because eta times sigma I inverse is going to be big, right? So this means that at this particular coordinate, we can actually allow this gradient updates procedure to have a huge jump in that coordinate, right? As long as change in that coordinate does not really affect the KO divergence between the two resulting distribution, right? So that is fine. So we can make a huge jump. We don't have to be conservative in these redundant, coordinates maybe. Right. So question, yes?
So intuitively, what is the Fisher information matrix telling us again?
Yeah, so this defines the local geometry, right? So this says that like, yes, okay, so let me just do this. Right, so this defines weights. So in this special case, this defines weights for every coordinate, right? So imagine that sigma 3 is tiny. So this means that the distance between the third coordinate is actually like not super important, right? Like I'm defining a new metric, which says that the deviation at different coordinates, they could be different, right? So Euclidean distance is just a special instance of this, which says that every coordinate is equally important, right? But Fisher information matrix says that every coordinate could be like, they could be like weighted independently, right? Maybe some coordinate doesn't really matter in terms of affecting the KO divergence. Like imagine you have some redundant coordinates, like changing in these redundant coordinates does not really affect the KO divergence too much, right? So you don't have to be conservative in these coordinates. Maybe just do a huge jump, right? Like you don't have to go like do small step gradient descent even in this redundant coordinates, right?
Yeah, that makes sense.
NPG allows you to do a huge jump in these coordinates, right? And NPG says that for those coordinates where the sigma I is big, meaning the relevant coordinates for KO divergence, then yes, we have to be conservative. We have to move very, very tiny, right? But for coordinates where the sigma is tiny, is approaching to 0, we can do a huge jump.
Thank you. Yeah, that makes sense.
I'm kind of confused. Wait, so if the sigma value is tiny, then it's a huge jump, and if it's large, then it's a small jump. Why is it not the other way around? I'm sorry, I'm confused.
Oh yeah, so this is sigma I inverse, right?
Oh, sorry, my bad.
Yeah.
Sorry about
this
that.
is like, let's write this way, right? Maybe this is easier to see, right? Okay, so let's look at this 1D example, right? Okay, so let's get some intuition on natural gradient on this 1D example, right? So this 1D example says that I care about a distribution, a distribution that parameterized by a single variable theta. Right, so this is just a softmax, a logistic, sort of logistic regression output, right? So this theta gives me a distribution, which is a 2-dimensional distribution, right? So this is, we can call this P1, this P2, right? And P1 plus P2 equals to 1. Right? And now let's see, I have an objective function, G theta, that looks like this, right? 100 times the first probability and 1 times the second probability. That's just my objective function. And I want to maximize this. All right, so what's the maximum, what's the argmax? G theta. Right, what's the theta actually maximize this function, G theta?
1, 0.
No, theta is a scalar, right?
Oh,
I mean, you're right. 1, 0 means the solution for this distribution, but what's the corresponding theta to achieve 1, 0? So you're right? So P theta star 1 should equals to 1, and P theta star 0 should be equal to 0. Right? Because I should put all the probability mass on the first coordinate, right? Because the first coordinate is worth 100.
Infinity?
Yeah, positive infinite, right? So this should be the positive infinite, right? Because when I put positive infinite inside this expression P theta, then the first coordinate just goes to infinite, and the second coordinate, the first coordinate just goes to 1, and the second coordinate just goes to 0. Right? So why this is true? Because limit of theta approach to positive, exp theta. Right? So this is just exp theta, just equal to 1. Right, so put it in other words, this is my scalar, one scalar theta parameter, right? And I know that the optimal solution is on this positive infinite side. right? So this is my optimal solution for this objective function. Right? So one potential way to optimize this function is actually do gradient ascent, right? So we can do gradient ascent, right? So if you're here, we're just gonna do small step here, small step everywhere, right? And it's gonna take us forever to get to the positive infinite side, right? Because gradient descent says that, you know, just do small step every time step, right? So we are being very conservative every time step. We just move a little bit, you know, every time. So it's gonna take us forever to get to the optimal solution. It eventually will get there, but it's gonna take forever, right? And now we will see actually if we do NPG, we will actually do a huge jump, right? So we're gonna actually make more and more aggressive updates if we gradually approach into the optimal solution. So NPG might look like this. I do a tiny jump, and gradually I do big jump, even bigger and even bigger and even bigger jump. So that's the NPG we'll do. All right, let's see, you know, if this is true. All right, so let's draw the picture for the distribution, right? So this is the distribution, right? So every theta on this line corresponds to a distribution on this segment, right? So this is a distribution. So this corner is the distribution of 0, 1. This corner is distribution 1 over 0, which we know is actually the optimal distribution at theta star. Right? So in other words, every point on this line, every theta 0 corresponds to a distribution, a well-defined distribution inside this segment, right? And particularly theta 0, if theta 0 equals to 1/2, then this distribution is just 1/2, 1/2, right? And it's the middle point of this segment. All right, so there's a 1-to-1 correspondence between a parameter theta and the distribution in this segment, right? And maybe when we do gradient descent, instead of worrying about the change in the parameter theta, maybe let's just worry about the change in the distribution, right? So we know that the optimal solution is here, and if you're here, maybe let's just follow descent direction here, right? Let's just make a small step in this segment, right? Like if I can just do gradient descent directly on this distribution space on this segment, right? I can quickly get to the global solution, right? This green dot, because this is a finite, like this segment has a finite distance, right? Like instead of doing gradient descent in the theta space, maybe let's do gradient descent in this distribution space in this segment, right? So that's the ideal case. And if we could do that, you know, that would be an ideal, right? Because we can actually do finite number of steps here, one more step, and a few steps, we will hit the goal, right? So this is actually different from doing gradient descent in the theta space because that's going to take us forever, right? So this is just really going to take us forever because the optimal solution is at the positive infinite side. Okay, so intuitively, this is what NPG is trying to do. Right, NPG is simulating gradient update in the distribution space in this line segment by making proper change in the parameter theta. Right? So let's see what's the Fisher information scalar is in this case. So the reason that I call this scalar because our parameter is a one-dimensional parameter, right? So it's not a matrix anymore. So remember the Fisher information matrix is, so if theta is R of d theta times d theta, right? So here my theta is just a scalar. So my Fisher information matrix is actually a scalar. So let's call it a Fisher information scalar. right? I've already computed this Fisher information scalar for you. So the Fisher information scalar at theta 0 is just this quantity, right? Again, what's the Fisher information scalar? So it will be the KL divergence of P theta 0, P theta, the second derivative of the KL divergence measured as theta equal to theta 0. Right, so this is the Fisher information scalar. Okay, I've already computed this for you. And let's check, what this Fisher information scalar is doing. So particularly when theta 0 approach to infinite, when theta 0 is really big, this Fisher information scalar is actually pretty small. Right? So one extreme case is that when theta 0 is positive infinite, this Fisher information matrix is 0. Right? Because the limit of theta 0 approach to infinite square, right? So this is going to be 0 positive, right? Because I have one exponential in my numerator and I have square, I have a double exponential in my numerator, right? So my numerator should increase way faster than my numerator should increase much slower than my denominator, right? Because my denominator has double exponential in theta. All right, so this means that if we just rewrite NPG update, so this is what we get, right? So we have the gradient scaled by the inverse of the Fisher information scalar. So in other words, this is our new gradient, right? So this is our new learning rate. So I can write this as theta 0 plus eta over f theta 0 g prime theta 0. Again, I scale my learning rate using my Fisher information scale, right? And I know that when theta approach to the optimal solution, my Fisher information scalar is actually approached to 0, which means my learning rate is actually pretty big. Right, so eta over f theta 0 approach to infinite when theta 0 approach to positive infinite. Right, so this allows us to do a huge jump, right? Because the more closer that we are to positive infinite, the smaller the Fisher information scalar is, right? Which means that 1 over the Fisher information scalar is actually big. This allows us to purposely scale up the learning rate, right? Because our learning rate is eta over Fisher information scalar. So if Fisher information scalar is a tiny quantity, then this learning rate is big, right? This is inversely proportional to the Fisher information scalar. So that actually enables us to do a huge jump, which means that if somewhere we are here, right, when theta 0 is pretty big, Fisher information matrix, Fisher information scalar, and the NPG actually allows us to do a huge jump. Right? I will get back to your question in a second. Let's compare to the regular gradient update, right? So the regular gradient update just ignores the Fisher information scalar and just do the regular update, which is the learning rate times the gradient, right? So your learning rate is fixed regardless of where you are, right? You're always doing very conservative small update every time step. So even if you here, the normal gradient, we're just to do a small update, right? But NPG potentially going to do a really big update because this is eta over f theta 0, right? And the gradient descent is just using learning rate eta. Right, this natural gradient ascent. Okay, question, yes.
So is it true in general that as we approach the optimum, the Fisher information decreases in like magnitude or size, and like isn't that something dangerous? Because like in this case, it makes sense that it's okay to increase the step size as you approach the optimum because the optimum is very large. But in general, isn't it better to take larger steps at the beginning and then slow down as you approach the optimum?
Yeah, so remember that we are not making very aggressive updates in the distribution space, right? Like we always start from the constraint on KO, right?
Oh, right, yeah.
Like imagine you do gradient descent along this segment. Like we are doing very tiny update here. It's just in order to realize a tiny update here. So we're here and let's do a tiny update to this step, right? So it's just in order to realize a tiny update in the distribution space, if we map it back, this might result in a very big difference between theta 0 and theta prime, right?
Yep.
But we are doing very conservative update in this, like in this segment, right? But we cannot directly control gradient descent on this segment. But what we can control is to control the parameter theta, right?
Yep.
And we know there's a 1-to-1 correspondence. So it's just that, you know, a small update here potentially could lead to a big jump here, right? So that's what Fisher information scalar is quantifying, right? Like if I make an infinitesimal small change in the parameter space, what's the corresponding change in the distribution space? That's what Fisher information matrix and the Fisher information scalar tells us, right?
Right. Okay. So I guess in this case, it's the case that it's telling us to make these larger steps in theta space as you approach that optimum value on the distribution. But in general, it would just tune itself such that you're making reasonable steps in distribution space by making whatever step.
Yeah. So the strategy you said is correct, right? I can gradually reduce down my KO. Like remember the KO divergence learning rate delta, right?
Yeah.
I can gradually shrink that delta. That is fine, which means that I'm doing slower and slower on this direction, right? When I'm approaching to the optimal solution. But this, I will just let Fisher information matrix to figure that out.
Got it. Yeah.
Right. All right. So just intuitively, you know, plane gradient ascent in the theta space will actually move to theta infinite at a constant speed. Right? So it's going to take you forever to hit this goal in the distribution space. Right? But natural gradient ascent says that let's just travel faster and faster when theta gets bigger. Right? So that's what Fisher information matrix scalar is telling us, right? Because this gets smaller and smaller when we approach it, to theta star, which means that in terms of the learning rate, which is eta over the Fisher information scalar, this learning rate is actually getting bigger and bigger, right? Because it's inverse proportional to the Fisher information scalar. Right, so that's why, you know, Fisher natural gradient descent and natural policy gradient could be much faster than the regular policy gradient.
So either way, whether you're doing the theta space or like the other space, it is going to have to slow down as it gets closer to the optimum solution, right? But if you do like the not theta space, it'll just like slow down slower, like. Yeah.
So remember that what NPG is trying to do is focusing on making update in this direction, right? In this space, in this segment. Like we can slow down the update in this distribution space, right? That is fine. Right, but the parameter space, we don't directly control it. Let's just let Fisher information matrix to figure out the change in the parameter space.
Is this idea also used in regular gradient descent for like supervised learning, for example?
Yeah, so you can use natural, it's called natural gradient. So you can use natural gradient for logistic regression, for instance. Right, so this is literally the logistic regression, right? So this objective function is logistic regression, right? Because this means that like I'm trying to classify it to class 1, right? Because class 1 is correct. It has reward of 100. Class 2 has reward of 1. So I should put all the probability mass on class 1. right? So this is a logistic regression, right? I'm trying to optimize logistic regression using natural gradient, right? Because in high level, what's really more important? It is the distribution that is more important, right? Like we should make, if we can make a gradient ascent in the distribution space, that's the most ideal case, right? But we can't do that, so we have to do an indirect approach. We have to control the parameters of the distribution in order to control the distribution, right? But maybe let's just figure out a good updated direction in the distribution space. All right, and then let's figure out what change we need to make in the parameter space in order to realize the change in the distribution space. Right, so this is really sort of this picture, right? So I want to move from this distribution to this distribution, p theta prime. This is theta 0, right? And this is very good because this is a correct and ascended direction in the distribution space. But we can't control the distribution directly, right? So let's just figure out what's the corresponding theta prime is. Right, so that's like, NPG is essentially trying to do, or natural gradient is essentially to do.
So I just have one question. I think at a high level, I kind of understand that the Fisher information matrix gives us some information about what like dimensions are important, essentially.
Yeah.
But what I don't quite understand is how the definition of a Fisher information matrix allows it to do that. Like, why is it that sigma 1, sigma 2, sigma 3 are defined in this way? This is my question.
So in general, Fisher information matrix is not necessarily going to be a diagonal matrix, right?
Yeah, right.
So that essentially, so in general, Fisher information matrix allows you to identify a subspace where you can actually move very fast. Right. So what really matters is the eigenvalues of the Fisher information matrix. Right. So imagine you have some eigenvector whose eigenvalues is tiny. Right, which means that inside that subspace that defined by these eigenvectors, you can move very fast, right? But in the coordinates in the subspace where eigenvalue is really huge, that means you have to be conservative.
Yeah, I think I understand that, but like, okay, so can we just redefine what the Fisher information matrix is? It's the gradient of the natural log.
Yeah.
So is this the Jacobian?
It's not Jacobian. No, no, it's not Jacobian, right?
It's the.
It is just this like it's. So okay, so first of all, this is a positive. This is symmetric matrix.
Right. Yeah.
Right, and this is a positive semi-definite. Right. So it has eigen decomposition. Let's write this U sigma U transpose maybe. All right, so now let's look at the eigenvalues. So there are potentially some eigenvalues are big, some eigenvalues are small.
Okay. Yeah, I'm not really sure how to phrase my question, but once I figure it out, I'll get back to you.
Yeah. Okay. So let's maybe keep this question in mind, and let's just probably revisit that at the end of the lecture. All right. So, but this simple 1D example, we don't have to consider about matrix. We don't have to consider about eigen decomposition, right? Because everything is a scalar. So in that example, it pretty much demonstrates the benefit of a natural gradient, right? Because it allows you to move very fast. Okay, so that's basically the second part of today's lecture. And as I said, the detailed explanation of natural gradient or natural policy gradient is out of the scope. So we were just trying to get some intuition of why this makes sense and why potentially this could be helpful in practice, right? I think another good way to get intuition is actually try it out, right? You are trying it out in the homework, but try it out in terms of compare it to the policy gradient. So compare natural policy gradient and policy gradient, because along the way implementing NPG, you already implemented policy gradient, right? Just to do like regular policy gradient on this couple simulation and plot the curve and compare the curve of PG and the curve of NPG and see how it goes. Right? See actually if NPG is faster. Right, so that's another good way, to get your hands dirty and try to get an intuition from a more practical perspective. Okay, so I hope this intuitive explanation of NPG helps. But now let's just move on to a quick review of the policy optimization approach that we covered, in the past few lectures. Okay, so why we were interested in policy optimization in the first place, right? Because we were interested in solving problems where we have huge state space. Right? For instance, if each state is an image, and if the image has 3 channels, and where each channel is 512 times 512, right? So the total number of states in this video game, for instance, is that big, right? Because every pixel has values from 0 to 255. And now you have 3 times, 512 times 512, many pixels, right? So that's a really big state space, right? So we cannot do any sort of enumeration over states, right? This is not just doable in computation, right? And another thing is that we can only reset from the initial state distribution, right? So this is also a pretty realistic assumption because, we can actually just blow out of our car every day, from our garage, right? To collect more data. So we can reset from the initial state distribution. So these 2 assumptions basically forbids us to do this enumeration over state approach, right? We cannot write a for loop. Like we cannot put a car to every possible state and check what's going on, right? This is just not doable. Like we can only reset from the state initial distribution. And also the total number of states is so big, we cannot even enumerate all of them. Right? So that motivates us to use function approximation technique, right? So that's all we're doing. So for policy gradient, a very common approach parameterization people use is actually use deep neural nets, right? So this is just a function that takes the state as input and outputs a distribution over actions. Right. So the message that I kept saying is that a policy should just be treated as a classifier, right? With total number of, a many classes. The number of actions is the number of classes that you would use in a classifier. Right? As long as this classifier is differentiable, we can apply any policy gradient methods on it, right? So the one thing that we haven't talked about is actually what do we do for continuous actions, right? If I have infinite many actions, if my action is in RD, what parameterization we could use? One very common parameterization people use is this Gaussian distribution. Right? So I'm just going to parameterize my policies distribution using a Gaussian distribution whose mean is computed from this function, mu beta, and this is my covariance matrix, right? So this mu beta could be, again, a feed-forward neural network. Right? I'm using a neural network to define the mean of the Gaussian distribution, and I have another parameter for parameterizing my covariance matrix of my Gaussian distribution. Right? The reason that I use exponential alpha is because exponential of alpha is always a positive number, right? We want to make sure the covariance is always a positive number. Right? This is just different parameterization choice. You can do other things as well. Right. So in this case, the total parameter, all the parameter that we want to optimize is the joint of beta and alpha, right? So this is our parameter theta. Right. So this is a differentiable policy with respect to both parameter beta and alpha. Right. So in other words, gradient log pi theta as, this still exists. Right. So we can still do policy gradient methods on this. Like nothing stops us to use policy gradient on this continuous parameterization. And this is actually the parameterization people use for this kind of, humanoid robotic control, because here the action space is actually continuous, multi-dimension and continuous, right?
So is the point that we're sampling actions from this distribution?
Yeah.
Okay.
Yeah. So we know how to sample from a Gaussian distribution, right? At least we know how to sample from a Gaussian distribution. So we can still do A from pi beta alpha of this S, right? Okay, great. And the first attempt that we did is that we used this algorithm approximate policy iteration, right? So again, this is a very greedy approach in the sense that I'm trying to find a policy pi that maximizes the advantage, the local advantage against my current policy, averaged over the current policy's distribution. Right? Averaged over this distribution, and the advantage is defined with respect to the current policy pi t. Right? And in other words, we find a greedy policy that maximizes the local advantage, right? So remember that we talked about approach to how to maximize this, right? We use a reduction to supervised learning approach to do that. But if you recall the oscillation behavior, the picture that we showed, right? We could potentially end up into a situation where we oscillated between two policies. We never make any progress because this is a very greedy update, and the new distribution resulting from the new policy could be widely different from the distribution from the previous policy, right? So that actually could, in the worst case, could give us this oscillation behavior. Like we keep changing between two policies. And that could literally happen. Okay, so you can actually construct an MDP and show that actually happens. Right? So in other words, we cannot prove, like there's no hope we can show that this algorithm is giving us monotonic improvement. Right? So then attempt 2, what we did is let's just fix this abrupt distribution change problem, right? Let's just make sure that we do a very, very conservative update. Right? So what we do is that let's first compute this greedy policy. Right? So the policy that maximize the local advantage, but instead of commit to that greedy policy, let's just move towards to it a little bit. Right? So this is the expression that mathematically describes the intuition, right? The intuition of moving towards to the greedy policy a little bit. So we are at pi t, and this is pi greed, right? What we did is just move towards pi greed a little bit for a tiny step size. So this is pi t plus 1. Right? So this is a conservative policy iteration. And what we showed is that there's two nice properties, right? So the first property is that this is actually conservative in the sense that the distribution, the state distribution between two successive policies, pi t and pi t plus 1, under the L1 norm is actually bounded by this learning rate alpha, right? With an amplification of 1 over 1 minus gamma, right? Which means that if we're very conservative in the policy update, the change in the two distributions will actually be very tiny. Again, this L1 norm of the two distribution is the sum over all states of the absolute difference between two probabilities. Okay. And then what we showed is that using this incremental property, right, we can show that the policy actually is making progress, if the algorithm has not terminated yet, right? So this is monotonic, like a monotonic increase, monotonic improvement. All right, so this is great. Then we talked about a third attempt, right? So this is policy gradient on parameterized policy. So one downside of CPI is that you have to actually keep all the policies that you computed so far, right? So if each policy is really big, then you're gonna use a lot of memory to store them. This is not super nice. Maybe let's just try to do like a one policy, but a big one policy, right? Let's just keep one policy. So this is what policy gradient allows us to do, right? So policy gradient says that now I want to find the parameter theta such that the resulting policy pi theta achieves the maximum local advantage against my previous policy pi theta t, right? Same objective function. Like I just want to maximize the local advantage against the older policy, right? But, you know, directly committing to the most greedy theta in this case is also not good because we know that you're going to face the oscillation issue, right? So don't make too greedy update. Let's just make a small update. So here it means that let's compute the gradient of this objective function and move along the gradient a little bit. Right? So in other words, let's locally improve this local advantage objective function a little bit by one-step gradient ascent. Right? So if you compute the gradient of theta of this local objective, right? So you will see this is nothing but just the policy gradient, right? Because this I can just do a one step of importance weighting. Right, so I just did a one-step importance weighting. So now I get this ratio between two policies, right? Pi theta over pi theta t. And now if I push the log, the gradient inside the expectation, then I will get this gradient of the log likelihood, right? Which is exactly the expression of policy gradient using the advantage function. Right, so let's just do one-step gradient update. And when eta is small, we are making very conservative update on the parameters. Yeah, and in the extreme case, when eta is infinitesimally small, then gradient ascent ensures that we improve the objective function. Right, so that's just the property of the gradient ascent algorithm. Okay, so the last attempt is this natural policy gradient. Again, we are facing this objective function, right? We want to maximize the local advantage, but we want to subject to a constraint, right? A KO constraint saying that the new policy should not be too far away from the older policy in terms of the KO divergence between their trajectory distributions, right? So that's really the underlying optimization problem. And what we did is let's just define a Fisher information matrix, which is the matrix corresponding to the Hessian of the KO divergence, right? So this is the Hessian, right? And then we do a convexification, meaning that we linearize the objective function and quadratize the constraint. And this gives us the following NPG update, right? A linear objective function subject to a quadratic convex constraint, which allows us to compute the global optimal solution for this simplified, convex optimization problem. Okay, so I want to talk about the last attempt, which is a new attempt. So this is called a proximal policy optimization. So again, we have this objective function, right? We want to maximize the local advantage, but to ensure incremental update. So what we do here is let's just add a regularization. Again, using the KO divergence. right? So I want to maximize the first term. I want to change theta, but the second term says that I should not change it too much, right? Because I want to make sure the KO divergence to be small. So there's a regularization term that forces us to make not too big change, right? And this is a tuning parameter, lambda. This is a regularization tuning parameter. Okay, we just added regularization to force us to not change too much. Right, let's do another importance weighting and expand the KO divergence a little bit. So this is the objective function we're gonna get. Right, so this is the importance weighting. And here, I've already expanded the KO divergence for you. All right, so now you get an objective function that only depends on the parameter theta, right? And let's just do a few steps of mini batch stochastic gradient descent directly on this function L theta, right? To approximate the Argmax theta of L theta. Right, so we have this function, stochastic gradient ascent to approximately optimize L theta.
So why do we need this? If the Fisher information matrix from the previous algorithm, like that was giving us the right steps to make for each gradient value.
So this is an even faster implementation, right? So Fisher information matrix could be slow. F theta is in RD times D theta times D theta. Okay, what if your parameter is what if your policy is a neural network which has millions of parameters? Like we can't even afford to write down a matrix whose size is millions of times millions, not even mentioning invert, right? Like matrix inverse, the computation time is D theta to the cubic. Okay, try out to invert a matrix whose size is maybe like 50K times 50K in your MATLAB. All right, your MATLAB is gonna take forever to compute that. Right, so that's the trouble, right? Like, yes, NPG can work for low dimension problem, but like our policy potentially could have millions of parameters if you're using a deep net, right? So Fisher information matrix, we can't even write it down. Like it's just gonna take a while to write it down, not even mentioning invert it, right? That's not super good. But this version is just directly put a KO divergence constraint on the objective function as a regularizer, right? And then you just do gradient ascent on this combined objective function. And of course, this is the parameter you have to tune.
I see. So this is faster in terms of computation time, but not necessarily in terms of like number of update steps.
Okay.
And is there a comparison between like the optimal solution returned by this versus the
so they're almost the same. So if you're interested, you can look at this PPO paper. They have comparisons. I would say NPG and PPO, they're almost the same in terms of return the qualities of the policies, but computation-wise, PPO is actually more efficient, especially when you use neural nets, right? When you're using large neural nets, whose number of parameters is probably millions, right? So then PPO actually shows advantage in computation. Like this approach, PPO really allows you to leverage GPUs to do all these things, right? Because GPU is good at doing this gradient update, right? And like you don't want the GPU to do matrix inverse if the matrix has millions of parameters, right? You can't even store it actually, first of all. Right. Okay, so that's pretty much the end of today's lecture. So I just want to quickly mention that starting from Thursday, we're going to move to a slightly different topic, which is called imitation learning, or in other words, you can call it learning from demonstrations, right? The question is that, can we learn a good policy purely from expert demonstrations, right? No reward signal, just some expert demonstrations showing you how to achieve this task. Can we learn from these demonstrations, right? So this is actually a super practical topic. Like most of the time, like for robotics problems, like you're gonna starting from this approach, right? Like running RL on the real robot is actually challenging, right? Because like starting from a random policy, like this is not safe, right? But you can always ask, human to provide some demonstrations by maybe holding the arm of the robot, right? And let's just warm start from this imitation learning approach so that we get a very good policy at hand already, right? So this is important for safety issue and so on and so forth, right? Like applying a random policy on a robot, like good luck, right? Like you might gonna destroy something, you might gonna kill a person, you might destroy your lab environment, right? But learning from demonstrations is safe and it's also very efficient. We will talk about that, in the next few lectures.